students, today we are going to discuss about oxidation reduction titrations. In our pharmaceutical analysis subject, the one more titrometry analysis, that is oxidation and reduction titration. That means in the same reaction, it is going to see both oxidation as well as reduction. Okay. So the oxidizing agent will be there as well as reducing agent also will be there. So both oxidation as well as reduction are going to occur in the same chemical reaction. Okay, so that's why this is also called as redox titration. Okay, so let us see what are the definitions and what are the different types of the oxidation reduction titrations. So if you see what is the definition of oxidation, that is loss of electrons. Okay, so oxy means gain of oxy. You can remember in this easy way. Oxidation means gaining of oxygen. Okay, that means loss of electrons or loss of hydrogen. In terms of the electrons or hydrogen, if you see, you can say that loss of electrons is going to occur and loss of hydrogen is going to take place, but gaining of the oxygen is going to take place. That is called oxidation. So if you see the reduction, that means reverse to the oxidation, that is gain of electrons or hydrogen, whereas loss of oxygen. Okay, so this is going to be defined like this. Easily you can remember in this. So what is a redox reaction? Redox means both reduction as well as oxidation. Both reactions are going to occur with, then it is called as a redox reaction. Okay, so in our titration, if it happens means we are going to call it as redox titration. So one species is oxidized and another one is reduced. That means in terms of the hydrogen, if you are going to talk, so oxidation is loss of hydrogen in a species. Example, H2O, that is water, is oxidized to O2. Whereas in terms of the oxygen, if you are going to talk, gain of oxygen in a species. Okay, so loss of hydrogen or gain of oxygen. So example, magnesium is oxidized to magnesium oxide, MgO. Okay, that means O is additionally added. Oxidation means taking oxygen, right? So reduction means gain of hydrogen in a species. Example, oxygen O2 is reduced to H2O2. Okay, so in terms of the oxygen, if you are going to talk, loss of oxygen in a species, that is H2O is reduced to H2, right? So this is called as reduction. So it is, oxidation is gain or loss of hydrogen, but not H plus. H plus ions are not gaining or loss we are talking. Okay, so H, that means hydrogen atom is going to be occurring, whereas similarly in terms of the oxygen, if you are going to talk, that is oxygen is going to gain or loss is going to happen. Okay, but not the ions is going to take place. So in terms of the electrons, if you want to talk, oxidation means loss of electrons, gaining of oxygen, loss of electrons is going to take place. So magnesium is oxidized to magnesium oxide, one O is additionally added. That means magnesium from 12 electrons to the 10 electrons in Mg plus 2. That means loss of electrons is going to take place. That's why you are going to see the positive charge. 2 electrons have been lost. Okay. So reduction, if you are seeing gaining of electrons, that means oxygen is reduced to H2O2. That means oxygen from 8 electrons to 9 electrons. That means it is going to get the negative charge, negative electrons it is going to take. That means O2 minus 2, it is looking like this. Okay, so these are in terms of hydrogen, in terms of oxygen, in terms of electrons, we can define oxidation and reduction. So generally we know what is oxidation. So in terms of food, as well as if you see fruits and vegetables generally oxidized when left open in the air, right? So if you see example here, bananas, if you cut it and open in the air, it changes its color. That means it gets oxidized. Apple is also, if you cut it immediately, the iron present in the apple is going to be oxidized. Okay, similarly if you take the people, so like human people, okay, so they are also get oxidized. That's why most of the anti-aging drugs are going to contain the antioxidants. Okay, so what is the solution for this to prevent oxidation? That is seal in plastic wrap or more radicals, that means add lemon juice to the cut fruit, then the oxidation is going to be prevented. So in this way we can reduce oxidation criteria. Otherwise, sometimes you can also add some agents, oxidizing agents or reducing agents. So what are those oxidizing agents and reducing agents? Let us see. The substance that donates the electrons in a redox reaction is the reducing agent. Okay, in terms of the electrons, if you want to talk, that donates the electrons, which is called as reducing agent, whereas that accepts the electrons, which is called as oxidizing agent. Okay, so in this way we can define what is oxidizing agent, what is reducing agent. So clearly, if you see with chemical reactions, the examples, oxidation and reduction. So gaining of the oxygen, oxy means taking oxygen. So methane, CH4 plus 2 oxygen molecules, then CO2 is generated and water. Okay, similarly phosphorus, it is going to be oxidized, then it is going to phosphorus pentoxide is going to form. And if you take the sodium, if you left the sodium metal outside, it is going to be formed sodium plus. Okay, sodium ion is going to be formed. So loss of electrons, it is going to take place. So in terms of the electrons, if you are going to talk, so loss of electron is going to take place. That's why here Na plus has come. Okay, so hydrogen is going to act as reducing agent because in that reaction H2 undergoes oxidation. Okay, so whatever the agent, it is called as reducing agent, means it is undergoing oxidation reaction, or it increasing in the oxidation number from 0 to +1 +2 like this. Okay, that means what is oxidation number and everything we are going to learn in the next slides. So here you can say that water H2 is reducing agent, means it is going to undergoes oxidation. It's itself, H2 is undergoing oxidation. Okay, so reduction, if you talk in terms of the reduction, releasing or losing of the oxygen, it will releasing or losing of the oxygen from a oxide compound. So what are those oxide compounds? Here you can see CuO. Okay, CuO is a cuprous oxide, and H2, okay, it is acting as a reducing agent, means it converts the cuprous plus water. Here the reduction is going to take place, and if you see the oxidized compound, okay, ferrous oxide, trioxide, then if you see 3CO, then it is going to form the CO2 and iron. Similarly, if in terms of the electrons, if you want to talk, that is chlorine, by losing the electron, it is going to see like this 2Cl minus, negative charge is going to be coming. Okay, so it accepting the electrons. So Cl2 actually it is called as oxidizing agent because in this reaction Cl2 undergoes the reduction process. That means decreasing in the oxidation number from 0 to -1. Okay, here if you see the oxidation number is 0, that means no charge. So oxidation number, you can easily remember that the charge whatever it is there after ionization, that is called as the oxidation number. So here the oxidation number is 0, here it is, whereas -1. Okay, so here also if you see it is 0 and here it will come as +1. So either positive or negative. So reagents used in the redox titrations, these are oxidizing agents, reducing agents. If you see the examples for this oxidizing agents, potassium permanganate, that is KMnO4, well known oxidizing agent, that is which is if you are at all you are going to use this KMnO4 in the chemical reaction, it is called as permanganometry. So similarly ceric sulfate, that is ceric ammonium sulfate, if you use this one, that is called as cerometry. Whereas if you use the potassium dichromate, so it is called as dichrometry, and that means titrations in the different titrations. If you are based on the oxidizing agent or titrant we are going to use, so based on that these are the names: permanganometry, cerometry, okay, dichrometry, iodimetry and iodometry. If at all you are going to use the iodine solution, then these are two types: iodimetry and iodometry. Next, potassium iodate, potassium dichromate, potassium iodate. Similarly, two types will be there. Okay, and potassium bromate is also there, that is called as bromatometry. So based on this, they have categorized in different topics. Next, if you see the examples for the reducing agents, ammonium iron sulfate hexahydrate. So it is also called as Morse salt. So FeSO4, NH4 twice, SO4, 6H2O. Okay. Similarly, iron ethylene diamine sulfate, it is called as Osper salt. And one more example, sodium thiosulfate pentahydrate. Okay, and arsenic trioxide, this is also called as arsenic oxide, AS2O3. So sodium oxalate and oxalic acid dihydrate. Okay, so these are the examples of the reducing agents. Sometimes metals are also going to be used as reducing agents, and antioxidants are also going to be used as reducing agents. That means ascorbic acid example, which is used to prevent the browning of the fruits by inhibiting the air oxidation. Okay, that's what we have seen in the previous slides. So what is oxidation number? So rules for assigning this oxidation number, if you see, there are different 9 rules for giving the oxidation number. If you see, first rule, the oxidation number of any uncombined element is 0. It is going. So these are the real rules. You need to remember all these rules. For each rule, we have given one example here. So oxidation number of sodium. If you leave the sodium in the open air, it will gets converted into another ion. So, but if you see sodium metal itself, the oxidation number is 0. So the oxidation number of second rule, that is monoatomic ion, equals the charge on the ion. That means, so like the Cl minus, okay, so monoatomic ion, Cl minus, that is -1, right? Next, Na plus, that is +1. Similarly, third rule, that is the more electronegative element in a binary compound, that is assigned the number equal to the charge it would have if it were an ion. So oxidation number of oxygen in NO is -2. Okay, so similarly, all these whenever there is a charge on the ion, that indicates the oxidation number. Okay, so all these are the 9 rules you need to remember. So if you see one more example, that is the sum of the oxidation number of all atoms in a polyatomic ion equals the charge of the ion. That means if you take the example of phosphorus, we know that that is a polyatomic. Okay, it is exist in different forms. So in H2PO4 minus, it is going to be the phosphorus. Okay, the oxidation number for this phosphorus is +5. It is going to form the P in +5 state. Okay, so these are the different rules for assigning the oxidation number. Now, assigning oxidation number to the elements in the following compounds. Let us see one example. So if you take this lithium dioxide and HNO3, nitric acid, Cr2O2 -2. Okay, let us see one example. So by rule 2, so what is rule 2? The oxidation number of monoatomic ion equals the charge on the ion. Okay, so we see that lithium has an oxidation number of +1, lithium plus, and oxygen oxidation number is -2. Okay, so HNO3 similarly, nitric acid yields H plus and NO3 minus ions in the solution. So from the rule 4, so what is rule 4? Let us see again. The oxidation number of fluorine in a compound is always -1. If you take fluorine at anywhere, the oxidation number is only -1. So here if you see, according to rule 4, we see that H, that means hydrogen, has an oxidation number of +1, and the other group, nitrate ion, must have a net oxidation number of -1. That means oxygen has an oxidation number of -2. If you see, the oxidation for the number for the oxygen is -2, and if you use X to represent the oxidation number of this nitrogen, then the nitrate ion can be written as N to the power X O3 to the power -2. That means here the number of oxidation state we are going to, it is not called as power, but just I am telling the for the better understanding. Okay, so that the X plus 3 of -2 is equivalent to -1. Okay, because whatever this X condition, if you want to know nitrate ions, it is going to have the oxidation number of -1. Okay, so here 3 into -2 means -6, -6 and this X value. Okay, so finally if you are getting +5, that means the HNO3 yields the oxidation number. How it is going to assign the oxidation number? That is +5, right? Generally if you see, assigning the oxidation numbers to the all elements means for each element you should know what is the oxidation state, how it is going to be converted into ion, and how the whether positive or negative charge is going to be there, right? So HNO3 minus, it is going to have the oxidation number of +5. So from the rule 6, if you see, the sum of the oxidation numbers in the dichromate ion, that is Cr2O7 -2, must be -2, right? So if you see the rule 6, the oxidation state of hydrogen, chromate ions, So mostly examples, if you see here, chromate ion is not mentioned, but the oxidation state of hydrogen ion in most of its compounds is +1, and unless it is combined with a metal, in which case it is -1. The hydrogen is going to change. Generally it is +1 only, but whenever it attaches to the metal, it is going to give you the -1. Okay, so if you see the oxidation number of oxygen is -2, so all that remains is to determine the oxidation number of chromium, which we can call this one as Y. So that a dichromate ion can be written as, here how we have written for the HNO3, similarly Cr2O7 dichromate for the dichromate ion. Okay, so Cr2O7, and for this Cr2 it is going to be called as Y, and for O7 it is -2, and totally -2 will be there. So if you are going to calculate for 2 Cr molecules, 2 into Y plus 7 into 7 oxygen molecule, -2 will be there. So after solving this, you are going to get the +6, right? So for the dichromate ion, you are going to get the oxidation number of +6. This is how we can calculate the oxidation numbers. Now coming to the, when a reducing analyte is titrated with iodine, okay, so iodine, we know that it is going to be used as antiseptic solution, and a lot of applications are also there. And the method is, whenever this iodine is used, that is called as iodometry, and sometimes which is going to be used as oxidizing agent and reducing agent also. Then the difference you are going to see, that is iodometry and iodometry. Okay, so first of all, let us see what is iodometry. So quantification of ascorbic acid, that is vitamin C. Ascorbic acid is vitamin C is present. Okay, so if you see this chemical reaction for the ascorbic acid, so whenever iodine solution is going to be used as a titrate here, so you are going to see dehydroascorbic acid. It is going to be converted to dehydroascorbic acid by a reduction process. Okay, so then iodide ions are going to produce and H+ ions are going to produce. So these are the structures. This is the ascorbic acid structure, and it is converted to dehydroascorbic acid. So this reaction is actually happening by reducing, okay, reduction process. So a reducing analyte will be there in the iodometry, as well as one single reaction it is going to take place, and here the titrant, that means the standard solution we are going to use, that is iodine solution. Okay, so iodometry means what is difference? The titration of the iodine, that is iodine produced when an oxidizing analyte is added to excess iodide. Okay, so that means the iodine is produced when an oxidizing analyte is added. That means during the reaction you are going to see the liberation of the iodine. That's why all the iodine reactions are going to take place in the dark. So iodometry is going to be performed in the iodine flask. Okay, normal conical flask you should not use. So iodine flask will be different, and also they need to be performed in the dark conditions only. It is going to be oxidized by the light. Okay, so then the iodine, which is usually titrated with the standard thiosulfate solution. Okay, so that means ammonium thiosulfate, sodium thiosulfate, like that. Okay, so by using those standard solutions, we are going to standardize the iodine solution. So iodometry means it is not a direct titration, because here there are two reactions which is going to occur. First of all, analyte plus iodide ion, it is going to be there, then it is converted to the iodine. So during the reaction, iodine is going to be liberated. First reaction. Then the second reaction, the liberated iodine. So how much amount of the liberated iodine is there based on the analyte, then that is going to be titrated with the standard thiosulfate solution. Then the final product is going to be there. Okay, so that means here the analyte is an oxidizing analyte, and here two reactions are going to take place, and similarly the same thiosulfate solution we can use it in iodometry as well as iodometry. So finally, analytical applications of this oxidation reduction titrations, if you see in this iodometric and iodometric, if you go into specifically for the titrations, for the iodometry, if you see analyzed species, that is reducing analytes are going to be used, and iodometry means oxidizing analytes. Okay, so here if you see the examples for the reducing analytes, that is species gets analyzed. Okay, that means reduction is going to take place here. SO2, sulfur dioxide, hydrogen sulfide, zinc, cadmium, mercury, lead. So all these estimations we are going to use this iodometry, okay, because these are the reducing analytes. So another example, drugs like cysteine, glutathione and mercaptoethanol glucose. That means and other reducing sugars, most of the sugars are also going to be analyzed by this iodometric titration. And iodometry means the species analyzed by in the iodometry, examples HOCl, bromine, okay. So iodates, all the iodate conditions, okay, oxygen and H2O2, O3, ozone is also going to be analyzed, and O2, okay, Cu+2 Mn permanganate ions, also these are going to be performed by iodometric titrations, okay. So these are the different applications of the iodometry as well as iodometry. So finally, let us see one example for this oxidation and reduction titration, that is titration of potassium permanganate against the oxalic acid. So here you can see both reduction as well as oxidation is going to take place, okay. So first of all, prepare a standard oxalic solution of about 250 ml. So oxalic acid, we know that it is a primary standard solution, okay, it is highly stable. So prepare an oxalic acid solution. The molecular mass of oxalic acid is calculated by adding the atomic mass of each constituent. So formula for the oxalic acid is H2C2O4, okay. So if it is available in the dihydrate form, then the molecular weight will be 126. Since the weight of oxalic acid that is required to make 1 liter, that means 1 molar solution, that is 126 grams. Hence the weight of oxalic acid we need only 250 ml. That means to prepare 250 ml of the 0.1 molar solution, go for the 126 divided by 1000 into 250. So how much molarity it is required, that is 0.1. So finally you are getting the weight of oxalic acid 3.15 grams. So the oxalic acid here acts as reducing agent, and KMnO4, which is going to be used as a titrant, okay. So KMnO4 acts as an oxidizing agent. Since the reaction takes place in an acidic medium, here the reaction is going to take place in acidic medium, the oxidizing power of the permanganate ion is increased. This acidic medium is created by addition of dilute sulfuric acid. That means whenever oxalic acid is weighed and prepared in the 0.1 molar solution, so certain amount 10 ml or 20 ml you are going to take in the conical flask. In that you need to make the solution to the acidic, that means dilute sulfuric acid, you need to add it. Then KMnO4 itself is going to act as an indicator because it is a pink colored solution, we know that, where the permanganate ions are a deep purple color initially. So in this redox titration, permanganate ions MnO4 is reduced to colorless. Reduction, okay, reduction is going to take place because it is an oxidizing agent. So manganese ions, so permanganate ions are going to be reduced to the colorless manganese ions Mn+2, right. So in the acidic medium, so the last drop of permanganate gives a light pink color on reaching the end point. So if you see the chemical reaction taking place in this reaction, that is KMnO4, 2 moles it is going to react with 3 moles of the H2SO4. So it is forming K2SO4 and MnSO4, okay. So this is the first reaction it is going to take place. So afterwards this oxalic acid is going to react with the oxygen liberated, it is forming the CO2 and water, okay. So this is a reaction, and afterwards how this oxidation and reduction is going to take place, let us see. So KMnO4 with H2SO4 and oxalic acid, right. So in presence of H2SO4, this KMnO4 is going to react with the oxalic acid, then this MnSO4 and K2SO4 are going to form. So afterwards anyhow water and CO2 are going to be byproducts. So ionic equation, if you are going to see that is permanganate ions are going to undergoing addition of the hydrogens, okay. So that means addition of hydrogen means loss of oxygen is going to take place. So this addition of electrons, addition of hydrogen, addition of electrons, it is going to be converted into reduction process, that is Mn+2 ions. So that's what they said here, colorless manganese ions, okay. So manganese ions are going to be occurring, so that means reduction is going to take place here. Then C2O4 -2, that means oxalate ions are converted to CO2, again electrons are going to be reduced. So this is a ionic equation. So finally the complete reaction is permanganate ions are going to takes place, again reduction, that means hydrogen, acceptance of the hydrogen is going to take place with the, and this oxalate ions is here you can see again manganese ions and water and CO2. Okay, so finally due to the manganese ions only you are going to see the pink color. Okay, so actually this permanganate titrant, whatever the solution we are going to prepare and use it as a titrant in this reaction, that is deep purple in color. Okay, but whenever we are going to add that solution in the conical flask which containing oxalic acid, the color disappears, right? So at the end point what happens, all the this MnO4 permanganate ions are going to be converted to the manganese ions. Okay, so that's why that manganese ions are going to have the light pink color. So at the end point you are going to see the stable light pink color. Then you can say that the reaction has been completed. So all the reduction is going to takes place in that, and oxidation, both oxidation as well as reduction is going to occur. Okay, so KMnO4 which is going to act as an oxidizing agent here, and oxalic acid it is going to act as a reducing agent here. So both oxidation as well as reduction is going to takes place. That's why it is called as oxidation reduction. Okay, so similarly different types of the titrations like potassium iodate, potassium bromate, potassium chromate, okay, cerulic ammonium sulfate. So all these solutions whatever we are going to use as titrant solutions, so in all the cases you are going to see both oxidation as well as reduction process. Okay, so this concludes how we can perform oxidation reduction titration. These are very easy, but just you need to know what is a chemical reaction is going to take place, what is an oxidizing agent and what is a reducing agent. So these are the basics about oxidation and reduction titrations. Okay, thank you students for listening.